Features of the cosecant and secant graphs. Now that we have our basic shapes, let's look at some of the details. How about the period of these two functions? Well, it's pretty simple. In each case, the period simply matches that of the corresponding reciprocal function. For example, here's our typical hill and valley of the sine function, ending us at 2 pi. Well, the cosecant function follows that same pattern. There's an upward U shape at the hill, there's a downward U shape at the valley, and then the whole thing just starts over again. So the period, of course, is the same. It's just 2 pi. It's a similar idea here. Here's one period of the cosine function, the vase we like to call it, again ending at 2 pi. Well, during that portion of the cosine graph, the secant graph has a half an upward U, a full downward U, and then another half an upward U, and then the same thing starts all over again. So of course, again, the period would be 2 pi. It's probably a good idea to keep a basic visual picture in your mind of these two functions. For the cosecant function, I would think about this, an upward U and a downward U matching the hill and valley. For the secant function, I would picture this, that downward U in the middle and then half an upward U on each side, again matching the shape of the cosine function. Okay, let's talk about the range of these graphs. The range is a list of all the possible y values you might ever see. Now we're just focusing on the blue graphs here. Of course, these y values here go off to positive infinity, and these y values here go down to negative infinity, so you might be tempted to say, oh, it's just all real numbers. Every y shows up. But if you look more carefully, here's 1 and here's -1. There are no values on the blue graph between those two spots. You only have 1 and above or -1 and below. So to state the range, we can use interval notation. We're going to have to do it in two pieces. We would say everything from negative infinity to -1, including the -1, so I'll put the bracket there. Then we use the union symbol. That just means or in math. It just means we're adding another section. And now we'll start at 1 and go up to positive infinity. Again, the 1 gets the bracket because 1 itself is included. What about for the secant function? Well, a quick look reveals it's the same thing. Here's 1, here's -1. Once again, we have no values on the blue graph between -1 and 1, but all the other ones are covered, and so we would simply have the same range for the secant function that we had for the cosecant function. So the period and the range were the same for both functions. Here's a couple of features that are different for each one. Let's start with the location of the vertical asymptotes. Vertical asymptotes, of course, are vertical lines, so all of the equations are going to be x equals a number. For the cosecant function, we have one at 0, pi, 2 pi, then 3 pi. On the negative side, if we extended this out a little bit, we would find the first one at -pi, -2 pi, etc. So we could summarize that by writing x equals 0, positive or negative pi, positive or -2 pi, and so on. There is even a shorthand way of writing this. We would say x equals any multiple of pi. Any multiple of pi. K here just stands for any integer. In other words, k could be 1 or 2 or 3 or -1, -2, -3, and if you fill those in, you'll get the entire list. So this statement here sums up the location of all the vertical asymptotes for the cosecant function. It's a little bit different for the secant function. Here we have asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, same numbers on the negative side, -pi over 2, and so on. Let's jot those down. So can we write a shorthand one for this? This seems a little more difficult. Well, we can. The key is to think about the distance between successive asymptotes. It's clearly the same distance. I could find it by just subtracting 3 pi over 2 minus pi over 2 and seeing what that distance is. It is, of course, 2 pi over 2, which reduces to pi. So this distance between each set of asymptotes is pi. Well, I can use that fact to help me write a simple equation for all of these asymptotes. Simply take the simplest starting one, I think that would be positive pi over 2, the easiest one, and then from there add on multiples of that distance, that pi distance we just found. For example, if you take pi over 2 plus 1 pi, you'll get 3 pi over 2. If you take pi over 2 plus 2 pi, you'll get out there to 5 pi over 2. If you took pi over 2 minus 1 pi, you'd get over here to negative pi over 2 and so on. Once again, k just represents any integer. So this formula sums up the location of all the vertical asymptotes for the secant function. This idea of using the starting value plus multiples of the distance is an important one. We could have done the same thing even back on the cosecant graph. The nicest vertical asymptote, well, that would have been the one at 0. And then the distance between, well, 0 to pi, that's pi. Pi to 2 pi, that's pi. It's pi once again. If I had written 0 plus multiples of pi, well, that's going to simplify to be exactly what we got. The 0 doesn't matter. I would have ended up with just x equals k pi. One other comment here. What if I had been interested in the domain of these functions? Domain means a list of all the possible x values you could ever use. Well, the thing is, there are certain x values you cannot use, and those are the places where we have vertical asymptotes. Those are the values of x that you cannot stick in. They make the function undefined. In other words, what we're saying is x can be any number you want except the spots where the vertical asymptotes are. The way you write that is like this. X is anything but multiples of pi for the cosecant function. Or in the case of the secant function, the domain would be x is anything but pi over 2 plus multiples of pi. So you can see if you can find the vertical asymptotes, you already then know the information about the domain. Another feature that's different between the two graphs is the symmetry. In each case, the symmetry matches the corresponding reciprocal function. So you might remember with the sine function, we said that the sine function was an odd function. This meant that the graph is symmetrical across the origin. In other words, if you flip the picture around 180 degrees, it will land on itself. Well, the same thing is going to be true of the cosecant function. If I spin this around upside down, it's exactly the same picture. And so we say the cosecant function is odd. It's symmetrical across the origin. What about the secant function? Well, looking at the graph of cosine, you might remember we tried to turn that picture upside down. It did not land on itself. So it's not an odd function. There was a symmetry, though, for cosine. If you fold the paper here along the y-axis, then the graph will land on itself. That's called being an even function, where the graph is symmetrical across the y-axis. And you can see for the blue graph, the same exact thing would happen. And so we say the secant function is even, it's symmetrical across the y-axis. Let's close by taking a look at how the graphing calculator handles these sorts of functions. So I'm in the y equals area. How about we graph the cosecant function? Of course, I don't have a cosecant button, so I'll have to type it in 1 over sine of x. And then just to match the other picture we saw, how about I add in the regular sine function as well, the reciprocal function. I imagine the z trig option will give me a pretty good window, so I'll choose that. And sure enough, you see that same familiar picture we were just looking at. Remember, z trig counts by pi over 2's here on the x-axis. So here I am down at 2 pi, 1 full period of sine, as well as 1 full period of cosecant, the upward u and the downward u. The only thing the graphing calculator doesn't show is the vertical asymptotes. You have to understand that they're there, and certainly if you're drawing the picture on paper, you're expected to show those as well. I'll leave it to you to try out the cosine and secant graphs on your own. Thanks for watching.